Okay, so in this one we revisit the example of 15.6.5 and do it legit in spherical coordinates. So we are looking at this integral of square root of x squared plus z squared, and our region of integration is bounded by y equals x squared plus z squared and y equals 4. And so there's a couple of things that immediately jump out at you, right? So you see that this is a hearty candidate for an r squared, and this looks like an r. And the fact that you are bounded by two equations of y is a fairly good indicator that doing a dy integration first would be a good idea. So let's go ahead and set that up. So our region looks something like this sideways opening paraboloid. And so if we're going to do a dy integral first, then imagine it being pierced by some line parallel to the y-axis. And you say, okay, so where do we first hit? Well, we're going to hit somewhere on this paraboloidal shell, and then we're going to leave out here through, so this is y equals r squared, and then we're going to leave out here at y equals 4, this disc-shaped end surface over here. All right, so then that tells us we're going from y equals r squared to y equals 4. And then let's see, and then once we've done that integral, you imagine yourself standing out here, looking this way, and saying, okay, so how does that project onto this plane that's parallel to y equals 4? And you see the shadow is this disk that's just a copy of the red one, basically. And so that's a disk of radius 2. So we have, let's see, r equals 0 to r equals 2. And then we do the full circle. So we've got theta equals 0 to theta equals 2 pi. Okay, and now we look at our integrand. And remember, the integrand never changes depending on how we on how we set it up with regards to the bounds of integration. So this is going to be r, and then we have an r for the Jacobian, and then we did our dy, dr, d theta. All right, so that's one way to set it up. That's the way that we set it up previously. Of course, now that we understand how cylindrical coordinates work, we could also set it up another way. So imagine if we first wanted to do r. So in this case, I'm going to redo that. In this case, suppose we are first going to do dr integration. All right, well, let's see. So where does it start and where does it begin? Well, it starts on the axis of revolution. So that's when we are at distance 0 from the axis. So that's where r is equal to 0. And then we stop out along this surface here where we have r equals paraboloid. Okay, so then we go back to our equations and we figure out, okay, so the paraboloid in this one is given by y equals r squared. So if I'm going to solve that, I get r equals root y. So r equals root y is going to be where we end. So for doing the innermost integral with respect to r first, we have r equals 0 at the core to r equals root y at the surface. And then let's see, so then we have to figure out, okay, so what does it look like after we've done this with respect to r? So the projection is maybe a little less clear as to what's going on, but what we have is this shape right here. So y, where does y come into it? Well, we're going to start here at y equals 0, and we're going to go, we pick up all these r slices until we get down here to the end at y equals 4. And so now what we've done is we've swept out this section of parabola, and then when we, so let me write this down. So we're going from y equals 0 to y equals 4. So now we've got this chunk O parabola, right? Kind of like a solid piece of parabola. Like imagine, I'm going to do like a little 3D sketch to maybe make it, I don't know if this is some other problem. But the idea is like we've got a little wafer of parabola like this. And then what we want to do is we want to rotate it around the axis of revolution, and it's going to sweep out the solid paraboloid. Okay, and so in that picture, this rotation goes this way here. So we go from theta equals 0 to theta equals full circle. And then the integrand is the same, r squared. And then this time we did dr first, and then dy, and then d theta. Now, this is not the preferable order of integration for this particular problem because, this one just looks a lot nicer to deal with, no roots, blah, blah, blah. But it may happen that you have some funky integrand. This integrand is a pretty nice one to deal with, but maybe it turns out that it's an integrand that's ridiculously awful to integrate with respect to y first. But if I integrate with respect to r first, then it somehow magically simplifies. Anyway, it's good to be able to use it or to set them up both ways.